So just a heads up, this next topic that we're about to talk about is, objectively speaking, one of the more confusing or the most confusing topics in the entire semester. So I let you know that so that you can pay extra attention and ask questions. So usually, at the end of this topic, after I've told students that it's one of the most difficult sections, usually students then say, well, it wasn't that bad. And usually it's because I scared them into paying extra attention. But it's usually true that this is one of the more confusing topics. So this topic is called the binomial probability. So let's first motivate this with an example. And the example here, a large part of it will just be review from what we've already talked about. So let's say that you have a multiple choice test of 5 questions. And let's say that you have 4 choices per question. So the first question we'll go over together, which should be review, is let's say you guess on all 5 questions. What's the probability that you'll get the first 2 questions correct and the remaining 3 questions wrong? So we'll notate it this way. So first 2 correct and the remaining 3 wrong. So this should be review. What do you think that probability is? Yeah.
1/4 squared times 3/4 cubed.
Okay, very good. So excellent. So we want this probability of this exact situation on this test, which means that we have to get the first question correct, and the second question correct, and the third question wrong, and the fourth wrong, and the fifth wrong. So these are joined by and because these all need to happen together in the same event, in the same test. So these are joined by and. So probability with events joined by and is which rule?
Multiplication.
Yeah, multiplication rule. So we would then multiply each individual probability by itself. So the probability of getting just the first question correct would be 1/4. And by the multiplication rule, it would technically be a conditional probability, which is the probability that the second question is correct, assuming or pretending that you got the first question correct. So if you got the first question correct, now you go to guess on the second question, what's the probability you'll get the second question correct? It turns out to be 1/4 as well, so this condition really didn't matter. So, because the events are independent of each other. And so, now the third probability is that you'll get the third question wrong, assuming that you got the first 2 questions correct. So assuming you already got the first questions correct, and now you guess on the third question, what's the probability the third question will be correct? Yeah, it turns out to be 3 out of 4. And same thing with the remaining probabilities. Probably you'll get the 4th question wrong, assuming the previous 3 events happened, is 3 out of 4. And the probability you get the last question wrong, assuming everything before it is assumed to be true, is also 3/4. So by the multiplication rule, we're just multiplying all these together. So another way of saying this is 1/4 multiplied by itself twice, or raised to the second power, times 3/4 raised to the third power. Okay, good. So this is a review. So the next question, which is new, and it's not reviewed, is what's the probability that you'll get any 2 questions correct? Not necessarily just the first 2 questions correct like before, but what's the probability that you'll get any 2 questions correct, and the remaining 3 will be wrong? So any 2 correct, which implies remaining 3 wrong. So before we talk about the actual numbers, do you think this probability should be the same as before, or if not, higher or lower?
Higher.
Okay, so a response for higher. What do the rest of you guys think?
Okay.
Higher? Higher? So anybody who said higher, why?
It'll be higher because instead of only the first 2 questions, it can be any 2 questions out of the 5, so there's more chances of that to happen.
Okay, excellent. So we're trying to find a probability here, which is the likelihood or the chances of this happening. And so if we're allowing for any 2 to be correct now, there's less restriction. And we're allowing for more things to possibly happen. So there's more of a chance of this new situation to happen now. So this probability should be higher than the previous one. Great. So now let's talk more about all the situations that could occur. So we're trying to find the probability of any 2 correct with the remaining 3 wrong. But just this situation, any 2 correct and the remaining 3 wrong, let's list out the possible situations that satisfy this condition. So, any 2 correct, remaining 3 wrong, let's notate it this way with specific questions of whether they're correct or wrong. So one way is the previous one we just did, where the first 2 questions are correct and the last 3 are wrong. That's one possibility that could occur, but there's one of many. So either that could occur, or what else could occur that satisfies the situation of any 2 correct, the remaining 3 wrong.
C.
Yeah, so instead of the first 2 correct, maybe now we get the first and the third correct, and the remaining 3 are wrong. Okay, so now instead of just listing out all these C's and W's, let's adopt a convention that's easier to work with. So, let's just keep track of which question numbers we're getting correct. So this is the same thing as saying 1, 4, or 1, 2, because any number we're not listing means that we're getting the question wrong. And here, it would be 1, 3. So let's just keep track of the question positions that we're getting correct. So what else could happen?
1, 4.
Yeah, 1, 4, 1, 5,
2, 3.
good.
2, 4. 2, 5.
3, 5. 4, 5.
Okay, is that all of them?
I believe so.
Okay, so how do we know for sure how many there are in total without having to list them all out like this?
Rule of counting.
Yeah, rule of counting, good. So each of these possibilities has how many objects in them? 2. So now you have these 2 placeholders. How many options for the first placeholder indicating the first question that you're getting correct? Yeah, 5 options for questions. And once you choose a question number that you get correct, how many options for the second question that you get correct? 4. Yeah, 4. And if you were just to multiply these, that would imply that the order of these 2 objects within these 2 groups matters. Should the order matter? Like, should you list out, if we have this, for example, 1 and 5, we notice that 5, 1 isn't listed here. That means that the order doesn't matter. But in this case, why didn't we list out 5-1? It's the same, two questions that we're getting correct. We've already listed out these two questions we're getting correct. So we only care about the identity of the questions we're getting correct. We don't care about the order. That's why we didn't list out 5-1. So because we didn't list out the different orderings, the order doesn't matter. And instead of just multiplying these two, we need to now divide out by 2 factorial. And another way of saying this is 5C2. Yeah, this is a combination. So 5C2 means the same thing as 5 times 4 divided by 2 factorial. And 5 times 4 is 20, divided by 2 times 1 is 10. So the total number of possibilities here is 10, and we listed out exactly 10. So there's no more other possibilities. All right, any questions? Okay. So the total number of possibilities here ends up being 5, choose 2, or 10. So that means that any one of these possibilities could occur, and there's a total of 10 of them. So if we have a probability with or, where any one of these could occur, then which rule is that? Addition rule. So that means you can add up the probabilities of each of these separate events. So now this will end up being the probability of the first event, CCWWW, plus the probability of the second event, which is, yeah, the first and the third, plus the probability of the third event, which is 1 in 4 being correct, and so on, until we have a total of 10. Now, how do we find the probability of each of these separate events?
Same way we found the first one.
Yeah, so how do, so why are these other probabilities exactly the same as the first one? So the first one, we just every time we saw a probability of a C, we just multiplied by 1/4. Every time we saw a probability of a W, we multiplied by 3/4. So the first one ended up being 1/4 squared times 3/4 cubed. But how do we know the remaining probabilities are the same?
They're independent.
Yeah, because it turns out that every time we see a probability of C, we're multiplying by the same number 1/4 because they're independent. Whether you get a question correct is independent of whether you got it correct previously. And anytime you saw a probability of W, you multiply by 1/4 or 3/4. And there are 3 of these W's and 2 of these, there's 3 of these W's and 2 of these C's. So you're multiplying the probability of getting a question correct twice. You're multiplying the probability of getting a question wrong 3 times. And when you're multiplying numbers, the order of multiplication doesn't matter. So either way, it simplifies to multiplying this 1/4 twice and multiplying this 3/4 3 times. So these remaining probabilities end up being the same as before. So, and you're adding each of these probabilities up a total number of 10 times. So if you add up a number 10 times, another way of saying that is 10 times the number. So in this case, the final answer will be 10 times what this probability is. But where did this 10 come from? The 10 came from this expression of 5 choose 2. So this represents the probability of getting any 2 questions correct and the remaining 3 wrong. So this is the final expression. So the final answer, you notice, has 3 components associated with it. So if, let's start with this middle component first. So it has this middle component, which represents the, quote, success component. Because we take the probability of success, which is 1/4, getting a question correct, and we multiply by the number of questions we want correct, or the number of successes, that was the 2. So we're taking the probability of success, or getting a question correct, and raising it to the second power, corresponding to the number of successes we want, 2 here. So this is the success component, and if we want 2 questions correct, that means that out of 5 questions, we have to get the remaining 3 wrong. So then we have this other component here that we call non-success. So success is just whatever you're keeping track of, versus non-success is what's left over. So here you're keeping track of getting 2 questions correct, and what's left over is that you're getting the remaining 3 wrong. So I call these terms success and non-success. Your book actually calls them success and failure. I think that's a bad thing to call it, because failure implies that it's not good. You're like assigning some subjectivity to it. And then students often get confused as, is this good or is this bad, or is this success or not? But really, success is just whatever you're keeping track of, and non-success is what's left over. So here you're keeping track of getting 2 questions correct, and what's left over is you can get 3 wrong. So, so you have the success component, the probability of success raised to the number of successes, and then you have the non-success component, the probability of non-success, or getting a question wrong, raised to the number of non-successes. And then lastly, you have this third component, which is this counting component, which you saw is important, because if we want any 2 questions to be correct, that means that you can have all these possibilities of question numbers that you're actually getting correct. So you actually have to add up all these possibilities together, and that's what this counting component does. So you actually have these 3 components. This is a specific example of something that we call a binomial probability. So in a binomial probability, you're answering the general question of finding the probability of any 2 successes out of any x successes out of n trials and it turns out that if you're trying to find a probability with this structure, then there's a formula that you can use, and the formula ends up being n choose x times p to the x times 1 minus p to the n minus x. The first time you see this formula, it'll be hideous, but if you relate it to the example we just did, you can really build this formula up piece by piece, and it's really no big deal. So, where p here is defined as the probability of success per try. So this is the general formula for the probability of any situation that has this structure, which is the probability of any number of successes out of another number of trials. In that case, as long as assumptions are met, which we'll talk about later, you can use this formula where you're just plugging in numbers. So let's apply this formula to the situation that we just did. So the situation we just did, we were trying to find the probability of getting any two correct out of 5 questions. So you see that in this example, the structure is very similar to this general structure here. So we have any number of successes. So this 2 would correspond to the x. Getting a question correct would be a success. That's what we're keeping track of. Out of 5 questions, so 5 would be n. Try to do this. And then a question would be a try. So everything matches up in this template. So then now you can use this formula. So n choose x, what would that be here?
5 choose 2.
Yeah, it would be 5 choose 2. Times p, where p is defined as the probability of success. Here success is getting a question correct. That's what we're keeping track of. So what's the probability of getting a single question correct?
1/4.
Yeah, 1/4. So that goes here. Raised to the number of successes that we want. Yeah, that's the 2 here. That's the x. Multiply by 1 minus p. So 1 minus 1/4 is 3/4. And then raised to the n minus x. So n minus x will be 5 minus 2, which is 3. And you notice this is the answer that you would get from the formula. But if you're just plugging in the formula blindly, it's oftentimes more confusing than building it up from understanding. And so this answer is the same answer that we get from deriving it like we did before. So it's the same answer with these 3 components. There's this success component, the non-success component, and then there's this counting component. Any questions there?
Is the 1 minus p the 3/4?
Sorry?
Is 1 minus p the 3/4?
Yeah, that's the 3/4. This one minus p is 3/4, and specifically it's the probability of non-success, or the probability of getting the question wrong, I guess. Okay, any questions, guys? Okay, so in the quick 3 minutes that we have left, let me relate this to a real life example. So maybe this will kind of bring it down to earth. So when I was in college and getting ready to graduate, my college had career fairs on campus. So different employers and recruiters would go on campus to try to find quality candidates. And there would be interviews on the spot at the career booths where students would just stand in line to get interviewed on the spot. And so oftentimes what the companies would do is they would give as the first question, they would give a weed out question that they knew would eliminate 90% of the applicants. And then the applicants that remained, then they could continue to interview with more specific questions. And so the weed out question that I got from one of the companies was this one. So if you flip a coin 10 times, let's assume that the coin is fair. So you flip a fair coin 10 times. And what fair means is that you have an equal chance of getting heads or tails every time you flip. Another way to say it is if you were to flip this fair coin a number of times that approaches infinity, like 1 trillion times, then in the long run, you'll get 50% heads. But in the short run, it's not necessarily 50% heads. If you only flip it 10 times, you're not guaranteed to get 5 heads. So if you flip a fair coin 10 times, what's the probability that you'll get 10 heads out of, or not 10 heads, 9 heads out of 10 flips? So what's the probability you'll get 9 heads out of 10 flips? So what do you guys think?
You could plug that directly into the formula.
Okay, so why is it that you can use this formula? Yeah.
Cause the 9 heads would be the correct, the 10 flips would be like the questions, and then you just plug it in.
Yeah, excellent. So the reason is that this formula applies to any situation that has this structure. It's probability of any number of successes out of another number of trials. And in this case, we have something similar, the probability of a number of successes out of another number of trials. And we can use this formula. So, great job, guys. So that means you passed the weed out portion of this interview process. Because 90% of students give the total wrong answer, which is to take 9 divided by 10, and they say that that's the answer. They say 9 divided by 10 is the probability. And why is that wrong? Well, if the question was, what's the probability of 10 heads out of 10 flips, can you just take 10 out of 10 and say it's 10 out of 10, which is 100%? No, you cannot do that, right? So you can't just divide these two numbers. So instead, you would use this formula, because basically you're saying what's the probability that any of the 10 flips will give 9 heads. And so using this formula, you're gonna get, let's practice using the formula together. So there's gonna be this counting component, so it'll be what, choose what. Yeah, it'll be 10 to choose 9. And then there's gonna be this success component, which is the probability of success. In this case, success is what we're keeping track of, which is heads. So what's the probability of heads for a fair coin?
1/2.
Yeah, 1/2. And then you're gonna raise it to the number of heads that you want. Yeah, it'll be 9. And then now there's gonna be a non-success component. So 1 minus 1/2 will be 1/2. That's probability of tails. Raise to the number of tails we want.
1.
Yeah, 1. Very good. So that's it. So this is the probability of getting any of the 10 flips, 9 of them are heads.